couple of you are having problems with 2019 question 10C, so I'm just going to run through it really quickly. It says, this is the question, so it says when 3.17 grams of mercury thiocyanide, and it's given you the molecular formula here, is heated in a well-ventilated fume cupboard, it decomposes completely according to the following balanced equation. So the only piece of information we're given is that we have 3.17 grams of this. So if you were to convert that into moles, moles is always going to be the mass given to you in the question divided by the relative molecular mass. So to the periodic table, you'll get the relative molecular mass of HgSCN2. So using the periodic table here from the log tables, I can just see that Hg is 200 grams, and then in a bracket S is 32 grams, plus carbon is 12 grams, plus nitrogen is 14 grams, and you multiply all of that by 2. You can put the 2 in there. Okay, so 200 plus 2 times 32 plus 12 plus 14 gives you a total mass of 317 grams. So back to our relative molecular mass, number of moles is 3.17 divided by 317 gives me number of moles of 0.01 moles. Straight away I will probably put that up here just to remind myself of what I have. So I have 0.01 moles. Now the only thing I have from this equation is the ratio. It's the only thing I can work with. So you'll notice here I didn't include the ratio when calculating relative molecular mass. The molecular mass is just the mass of the molecule, not taking the ratio into account. But up here the ratio is important. So I have 2 of this mercury thiocyanide, I have 2 of this, I have 1, and I have 1. So this is the ratio that they are in to each other, which means that if I have 0.01 moles of HgSCN2, I have also got 0.01 moles of this. I have half that amount of CS2 because it's in a 2:1 ratio. So 0.01 to 0.005, likewise 0.005 here. So straight away from this balanced equation, I can tell the number of moles of each substance, reactant and product that I have there. The first question asks me for the mass of C3N4 produced in this reaction. Okay, they're asking you for the mass of it. So mass we know is equal to moles multiplied by relative molecular mass. We have the number of moles of it straight away because I've just found that out from the ratio in the balanced equation. So what I'm going to do there is go back to my periodic table and get the relative molecular mass of C3N4. So it's going to be 3 times the mass of carbon, which is 12, plus 4 times the mass of nitrogen, which is 14. And you get a mass of 92 grams. So 92 multiplied by 0.005 gives me a mass of 0.46 grams. So that's how much of it is going to be produced, and that is simply your answer. Part 2 then asks you for, it says how many litres of oxygen gas measured at STP are required for the complete combustion of CS2. Okay, well if I have 1 molar quantity of absolutely any gas at STP, I know that occupies 22.4 litres because you just learn that number off by heart. So if I have 1 mole of absolutely any gas at standard temperature and pressure, it will take up 22.4 litres. They're trying to ask me how many litres. Okay, so this is the question. How many litres of oxygen gas will be required for the complete combustion of CS2? Looking at the balanced equation again, you have CS2 here reacts with 3 times oxygen to give you carbon dioxide and sulfur dioxide. What I'm going to do is just write out that equation exactly as it is. So CS2 reacts with 3 times oxygen to give you CO2 plus 2SO2. From the balanced equation up here, I know that I have 0.005 moles of CS2. The question is asking me how many litres of oxygen will that react with? Well, if I was to just focus on this equation for a moment, I have 1 CS2 and I have 3 oxygens. They're in a 1:3 ratio. So if I have 0.005 moles of CS2, 3 times that amount of oxygen is going to be how many moles of oxygen I have, which is 0.015. That's how many moles of oxygen I have. Now, back to my first point, if I had 1 mole per litre of oxygen at standard temperature and pressure, it would take up 22.4 litres. I don't have 1 mole, I have 0.15 moles. So I'm going to multiply that by 22.4 litres to see how many litres of oxygen is reacting here. So 22.4 multiplied by 0.015 gives you 0.336 litres of oxygen. So in order for this reaction to happen here, it takes 0.336 litres of oxygen. 1 litre of oxygen is 1,000 centimetres cubed. Okay, so this is the same as saying 336 centimetres cubed of oxygen. Okay, but the question asked you actually how many litres of oxygen, so you can literally leave it in that format. And there's your answer. Okay, going on then, part 3 says, what is the number of mercury atoms produced? Okay, so you're looking at your 3 balanced equations again, and I can see this is where my mercury atoms are being produced. Now, the question asks you for atoms, so if it's asking you for atoms, you have to incorporate Avogadro's number. So what I would start off with is by looking at how many moles of HGS we have, and I'll know that from the balanced equation up here. So first things first is HGS, I have 0.01 moles of it. So HGS plus O2 gives you Hg, which is what we're wondering, and SO2. HGS here, I have 0.01 moles of it. The only thing I'm concerned about is the ratio of HGS to Hg. And I can see there HGS to Hg are in a 1:1 ratio, which means if I have 0.01 moles of HGS, I have 0.01 moles of Hg. The question asked you for how many atoms. Again, it's always good to remember, if I had 1 mole per litre of any substance, I will have 6 × 10⁻23 particles, be it atoms or molecules of that substance. I don't have 1 mole per litre, I have 0.01 moles, so I simply multiply that by 6 × 10⁻23, and when it will give me how many moles per litre, 6 × 10⁻23, it will give me how many atoms of mercury I have there. In the calculator, it's given me 6 × 10⁻21, so that's atoms of Hg. Okay, so the last part of the question is definitely the most difficult. It says, what is the total number of moles of gas formed? So if you look here, they've given you the 3 balanced equations in the question because they need you to use them. So you're going to be working with ratios throughout the 3. If you look at the first equation there, they've given you mercury. The small subscript L beside it means that mercury is a liquid at room temperature. The question has only asked you for the number of moles of gases formed. So you're only concerned about 1, 2, 3, 4, 5, 6 of the products being produced because, 1, 2, 3, 4, 5 of the products being produced. Of the 6 products being produced, only 5 of them are gases. So they're asking you to total up the number of moles of each of these individual gases being produced. Just to actually answer that question, I've rewrote out the equations because you would need to see the ratios for each of them in order to answer this. So from the initial first balanced equation, which was here, I can see how much of each product that I produced, be it 0.01 moles or 0.005. Those products are now my starting points, so they are now my reactants in these equations. So from the previous balanced equation, I had 0.01 moles of HGS, I had 0.005 moles of CS2, and 0.005 moles of C3N4. My question is literally just asking me to check the number of moles I have of each of these products being produced in relation to the ratios that I have. So first things first, with a green pen, I'm going to just look at the first equation. Hg here is a liquid at room temperature, so I don't care about it. SO2 here is a gas at room temperature. The ratio of HGS to SO2 is 1:1, which means that if I have 0.01 moles of reactant, I have 0.01 moles of product being produced. Looking here at my second equation now, I have CS2, I have 0.05 moles of it as a reactant. That is also in a 1:1 ratio with CO2, which means I have 0.005 moles of CO2 being produced. It's in a 1:2 ratio here with SO4, which means I have double that amount, 0.005 being produced, which is 0.01 moles. And in the last equation, this is where it gets a little bit more tricky because the ratios are not straightforward. So I have 2 C3N4 producing 3 of these and 1 of these. So if it was a 1:1 ratio, my 0.005 moles of reactant would produce 0.005 moles of product. Because it's a 2:3 ratio, the number of product I'll be producing here is 3 all over 2 of 0.005. Okay, so on a calculator, 3 all over 2 by 0.005 gives you, it's given to me as scientific notation on the calculator as 7.5 by 10 to the minus 3, but you know that's the same as 0.0075 moles. Okay, and lastly, I have a 2:1 ratio here. So if I have 0.005 moles of reactant, that's producing half that quantity of product, which would look like this. Now, the question initially actually asked me, what is the total number of moles of gas formed? What you can see here, so I'm after working out the molar quantities of each of the gases. Okay, so what I'm going to do is just literally add them together. So I have this quantity, plus this quantity, plus this, plus this, plus this. So that last question was actually not difficult, it was just really tedious to have to work out. So if you add them all up, 0.01 plus 0.005 plus 0.01, 0.0075 plus 0.0025. Make sure you put them all into your calculator correctly, and you should get 0.035 moles of gas products produced. Okay, so that's the final answer.